I'm going to talk about the digital thread and about some background material. I also like to get some feedback from everybody about your background and whether you've had any experience in manufacturing, and sort of tailor some of the content to what you need to know to be able to participate in the challenge. So a little about me. I am the Chief Strategy Officer of System Insights. That's my company. We do process analytics, so we do big data analytics on manufacturing, for manufacturing, primarily discrete manufacturing. I'm also the Chief Architect of MTConnect. So I've been working on this standard for 8 years, and I'm the one who actually writes a lot of the documentation and kind of puts together the structure and the protocol and everything else. So that's why I'm up here talking about it. And I'm also, has anybody heard of things like the Industrial Internet Consortium or Industrial Internet of Things and that kind of thing? Okay, IIC is, I'm also one of the chairs of IIC for analytics. So it's kind of my background. I'm from the financial industry, so I come out of developing large-scale financial systems for real-time risk management and trading systems and other fun things like that. So there's actually some similarities, but I'm not going to get into any of that. So back to it. So basically, the drivers for what we're talking about today, and why do we care about data, why do we care about manufacturing, is this. So if we look at the entire sort of field of Internet of Things, has everybody heard of the Internet of Things? A lot of it comes into consumer. So you hear a lot about things like Fitbit and various different devices, cameras you can put on your cat, all these kind of things. So that is one piece of it. But what often people don't realize, if you look at the way, this is actually a McKinsey report, and if you look at the breakdown of where the big money is, all along here, factories, manufacturing, operation optimization, predictive maintenance, industry optimization, $1.2 to $3.7 trillion of available value. So that's why we care. So we care because basically this is our biggest sector. If you look at all the other sectors, nothing even comes close to the size of manufacturing. They're all about half, even the biggest ones like health and so forth. So it's definitely something that we need to focus more on. And the problem is that a lot of the people who are in things like manufacturing engineering and some of the sciences don't cross over into some of the technologies. And that's where this is trying to encourage people to get the background in both areas to be able to apply some of the data and analytics to the manufacturing sector. So is everybody familiar with things like discrete manufacturing, differences between like continuous process and discrete?
I can guess, yes.
Okay, so get into it a little bit. Discrete manufacturing is where you have single parts that are made. So it's not a flow of material, like we talk about pharmaceutical and food, where you have these continuous flow of material coming through. And energies, where you're processing, usually pumps and automated machines, very bespoke, versus discrete manufacturing, where often you're doing things like metal removal or composite or something along that line, where you're dealing with an individual part that's slowly being transformed through multiple different processes to a final shape. A lot of our high-value manufacturing, things like automotive and aerospace, are all discrete manufacturing. So it's definitely one of the highest value areas of manufacturing in general. And the standard that I'm going to talk about, MTConnect, is actually focused primarily on discrete manufacturing. So discrete is basically taking something like here you have a raw forging of a drive shaft, you do a series of machining steps on it, you come up with a finished part, and then there's an assembly process where you put the various bits and pieces together. MTConnect, again, to even narrow a little bit further, is interested in that manufacturing step, basically the processes that are involved in either additive or subtractive material. So basically adding or removing material from various pieces of metal, plastic, whatever. And the other thing that we're concerned about, and we're getting into right now in a big way, is process flow. So if you think about things like the digital thread and how manufacturing is executed, it's not just on one machine. Basically, you go from machine to machine. There's things like this is actually the process for making a drive shaft. There's all these different processes, and each process is executed on a different set of machines. So there'll be travel time, part handling, setup and tear down of those different machines, and so forth. So we're concerned about basically all of these timings and how the process flows, how effective it is, and how optimally we're executing those different processes on those different machines. If we think about it from the standpoint of data, the machines on the floor are giving a huge amount of data out. So if you look at your standard like CNCs, lathes, and everything else, don't try to read it. I'll give you examples later, sorry. So you're getting a lot of data out of these different machine tools. But to be able to actually do some analytics and to be able to understand how the processes are performing, contextualized within the entire manufacturing process, it's not possible now because there's this barrier here between the information coming off of the machines and whatever kind of analytic applications you have. If we look at the entire market, we look at what's going on right now, 95% of the shops out there are what we consider dumb. Basically, data collection and even basic monitoring. Collecting data from machines, understanding what the machines are doing at any point in time is very low. Basically, the number of shops that are actually doing this, especially if you talk about the small to medium manufacturers, I'll get into those in a second, very few of them are actually doing anything even simple like monitoring. We have monitoring applications, a lot of those out there today. So this step here is not too hard to get to, but a lot of people are still using paper and pencil and stopwatches. The next step up is things like real-time analytics. That's when you take the data and you start analyzing the data and you start understanding what's happening, why is it happening. So you're able to take your basic monitoring, backward-looking reporting, and start to predict forward, like, okay, the machine is down, why is the machine down? Can we tell from the data and the context of the process why this machine is not operational right now? The next level you can go up to is proactive, where I can now say, I see that this machine is about to go down, let's do something about it. Let's alert somebody so it doesn't go down and we don't lose production. That's a proactive step. The next is predictive, where I can actually look at, okay, historically, when these sets of circumstances occurred, I can predict that this is what's going to happen in the future. So I can actually look at each one of the steps. I can see how the processes are laid out and how the interleave is going to happen. And I can see that there's a tendency, if I do this set of steps in this order, something bad is going to happen right around there. And now you can get more predictive about your maintenance, about your quality, about your yield, tooling, et cetera. The next step is where the systems actually start to self-optimize. So we're still talking about human-in-the-loop processes. Now we start talking about things like self-optimization, where you can actually have the processes figure out optimal strategies for being able to manufacture parts. It's not just where I'm going to have a set of pre-described weekly schedules. Now the system can work around various different congestion, maintenance issues, tooling issues, process issues in near real time or real time, make decisions, even decide, send it out, keep it in, these kind of things. Of course, the final is, where we start getting into, your T2 Cyberdyne type scenario where, machines take over the world and, kill all the humans. But that's to come later. So we're still trying to get to this step here. We're a long way from that. So anybody familiar with the small to medium manufacturer? Has anybody worked in like a shop or done an internship there? Okay, so a few people. That's good. More than I had last time. So small to medium manufacturers are typically companies that are below 500 people and modest revenues, but they do make up a large portion of our industrial base. So if you look at the number of firms, there's actually around 250,000 firms out there right now. So it's a huge number of these. This is in the US. This is actually a couple of years ago, census data. So there's a large number of these. They employ nearly 5 million people. There's a huge number of also ancillary companies associated with it too. If you look at on a total small business, it's number 4 here, not too far behind. So this is like health and then retail, food services and so forth. The manufacturing is way up there. And actually in money, high value jobs, it's pretty high as well. That's one reason why the government is focusing on this so much, because there's actually a need to be able to build and maintain this base in the US. So we think about how they interoperate with everybody else. So basically we look at sort of a supply chain tiers. Your OEMs are here. Those are big companies like Boeing who sell aircraft. But if you look at Boeing or GM or any of these other big companies, there's actually a huge number of tier 1s and tier 2s and all the way out to like tier 3, 4, 5 suppliers that come in and provide parts to those companies. They don't make everything themselves. Actually, a lot of innovations come out of your smaller SME shops. And like Itamco is a good example of it. That's actually the guy who won last time, Joel Neidig, who did the Google Glass thing. He works for Itamco, very creative guy. And they are a big supplier to Caterpillar. They do a lot of the huge gears and parts that go into Caterpillar equipment. So, and they're, I think, around a tier 1 or tier 2 supplier as well. And then, of course, you have the other direction, which is the customers and the supply chain going out this way. So you look at aerospace and automotive, there's these very deep, complex supply chains, redundancies built in. If you ever looked at anything like from Apple and Tim Cook, they have this, mesh of companies that supply parts and components so that, that can never go down. There's another type of SME also. I'm going to use Task Force Tips, actually a customer of ours, who makes water cannons and nozzles and really cool firefighting equipment. And they're actually in Valparaiso, Illinois, and this is another type, but produce very specialized parts, complex specialized parts, and they are the leader in this type of equipment in the world. So they're incredibly innovative, and they have fairly small production because there's only so many of these things that are needed out there, but they knock everybody else out. So there's these types of companies there. And this is, they deal with the complete product life cycle. So if we talk about supply chain SMEs, they're usually getting designs and requirements from other companies and then developing products for another company, versus these types of companies which are actually going from the initial ideation part where they think about what to do all the way down to the final product and then delivery and so forth. So that's kind of to frame the SME boundaries. One problem that we have with SMEs right now is technology. So if we look at your standard SME out there, there's not a lot of IT, OT staff. So if you look at the larger companies, they usually will have dedicated information technology groups and operational technology groups, and though that's sometimes even problematic in and of itself, a lot of these smaller shops don't even have sort of an IT department. They're just kind of pulling wire and hoping for the best. There's no real, a lot of the machines, people are afraid to actually hook the machines up because they're afraid that they'll get viruses, so they just keep them completely disconnected. That's called an air gap. Where you either completely isolate your operational network and don't connect it to anything, which limits the amount that you can do with it because you can't really get data off of that. You can't do any interesting analytics or use any services that are out there. And the larger ones also usually have some form of a firewall, but again, it's like the number of technology solutions you can bring to bear are very few. So that's where we start getting into some blockers. This is actually a small video on Digital Thread that shows you a little bit about on the design side of it, what some of the blockers are.
When it comes to manufacturing, we've come a long way since goods were made by hand. We thought we'd arrive when we could team up with machines to make things. Until we built machines that followed our orders and could work on their own. But one problem is yet to be solved. Even though today's machines are smart, they have trouble communicating with each other. They're like kids playing the game of telephone. Someone starts out a phrase that gets passed from kid to kid. But I admit, when I was a kid, I'd like to change it up a bit, just to have some fun. Even if I did behave, the message never came out the same on the other side. It's often the same with machines in manufacturing. A product's design starts out as a three-dimensional model. But if one machine doesn't have the right software, the design may have to be bumped down to a flat two-dimensional drawing. Then, the information must be re-entered by a human so the next machine can do its job. Details can get lost in translation, and errors can creep in. A mistake may not be caught until the part is delivered and doesn't fit or isn't what was intended. The results? Wasted money, wasted time, and stressed out workers. Here at the National Institute of Standards and Technology, we think we have a fix. The digital thread is a way for different machines in a manufacturing process to all follow the same set of digital instructions. Deviations are caught automatically, which ensures the end product is the same as the original design. I'm heading out to Middle America to see a digital thread pilot project in action. Iowa, a state that's all about corn and caucuses. Oh, and manufacturing.
Farming hasn't been the biggest thing since I was a kid. So now we've switched to high-tech manufacturing.
In the digital thread pilot, Gator Smart Machines will follow the 3D instructions supplied by Rockwell Collins to make a heat shield for an aircraft circuit board. If all goes as planned, each machine in the process will understand the same digital language. During each stage of production, the product is checked against the original design and any discrepancies are auto-corrected. I'm heading 42 scenic miles south, where it all comes together. At Rockwell Collins. We're going to see if the part produced by Gator meets the Rockwell Collins specs. If you want to talk about a company where accuracy is truly a life and death matter, look no further. Apollo, Gemini, Mercury, every mission used Rockwell Collins communication equipment. Here, getting things right is pretty important. Hey Kevin, what's going on in here?
Oh, hi Tom. Hey, we're just got done inspecting the latest Gator part.
How'd it turn out?
Oh, everything came out great. It's a perfect part.
Not on any unintended holes or anything. That's great.
This is fantastic. We can take the original model, feed that right into manufacturing and building the part, right into inspection, and the same model is used throughout the process to look at the part.
The digital thread. It just might stitch together the next industrial revolution.
Has anybody heard of this? There's this concept called IT/OT and a divide between them. Okay, so IT/OT is basically the information technology and operations technology groups. And if you think about it, your IT group is sort of, you know, they're maintaining the entire organization, the enterprise. They have their systems kind of locked down. They have the barriers and boundaries set for that. And there's only certain points of ingress and egress, and you can kind of maintain this and protect your system. The OT side, unfortunately, has taken this model here, where we've put each machine in sort of an island of automation. So the machines are separated from the rest of the environment, and there's only very limited amount of information, only limited entries and exits that we can actually use to be able to get data in and out of these things. And it's often very, very difficult, especially on some of the legacy and older equipment. One of the problems that we also have is that machines tend to last around 30 years, which is great because you pay a lot of money for them. They're very expensive, and a lot of them are excellent machines, and they do their job fine. But from a technology standpoint, trying to get data from those machines and understand what they're doing and how to make them more efficient. The old machines don't have any ports, internet, networking, basic Ethernet wasn't even around. So a lot of them hardly have Ethernet ports. It's either serial or you end up just getting 24-volt signals. And on some of the, let's say, 15-year-old machines, we have this other problem, which is that a lot of them were shipped with early versions of things like Windows XP and the early versions like SP0, which is just this virus magnet. You put it onto a standard network, and it becomes infected. Just the ambient viral load is enough to take it out. So you basically have to quarantine the thing. And that's where we get into this type of scenario where the OT staff basically quarantines the entire set of manufacturing equipment. The IT is out here where you have services and people and technologies and mobile apps and all the new tech that's coming out, as well as cloud-based services. So you have big data analytics and things like that are available at the IT level. But over here, because of this barrier, we really can't get any of the data out to be able to take advantage of these new technologies. So what we get into is a lot of very proprietary systems. So if we look at your standard OT type network, you'll have each one of these applications and each one of these technologies basically having a separate connection to each one of the devices out there. And it'll cost you a lot of money, it'll cost you a lot of headache, there's a lot of time and energy put in just trying to get basic connectivity so you can drive your business applications. The solution is really around standards, and so we're going to start getting into what we're promoting, what we do and why we support the MTConnect standard. Because if you want to get efficient systems, you want to get technology that's going to make manufacturing better, be able to compete. Has anybody heard of things like Industry 4.0 over in Germany, what's going on around the world in manufacturing? There's a lot of initiatives, like in China, Germany, almost all industrialized countries right now have some form of digital manufacturing project going on. I mean, Germany's probably the most prolific right now with Industry 4.0. The US has a few of them as well with DMDII and SMLC. But for us to remain a leader in manufacturing, because believe it or not, America still is a leader in manufacturing. We're actually way up there. For us to maintain that and even gain ground, we need to be more agile. We need to be ahead of the technology curve. And that means being able to take data and apply analytics to it so we can then reduce the cost, increase quality, increase the speed. So you have the standard trade-offs here. To be able to make those trade-offs and to be able to improve our processes, we need information. And that's where things like standards come in. So the MTConnect standard basically is a common way to get data from manufacturing equipment. So it provides a single point where you can get a vocabulary, a common set of words, a common protocol to get data from all of your manufacturing devices. It's free, it's open, all that good stuff. And a lot of the big manufacturing companies, a lot of the big machine tool builders have actually already implemented it, like Moriseki, Mazak, Akuma. A lot of these big companies have already done it. It's available for many other machine tools and controller types like FANUC and Heidenhain and so forth. So with that technology, you can start getting data from your manufacturing equipment, and then you can start applying it to, basically bridging that IT-OT divide. So starting to get the data out of your machines. And one of the things we talk about is basically pushing this boundary. So yes, I have these machines, they're vulnerable, they have issues, but can I push this boundary as far over as possible? So now, instead of quarantining the entire system, I'm now just sort of quarantining the device itself. So this is called edge analytics or edge security. And then we can start pushing the data out with standards and other technologies and secure protocols. We can start pushing the data out. And then we can start making use of a lot of these IT technologies that are out there, like cloud services, et cetera. And then there's a whole host of new technologies and new techniques that we can use. And that's part of what this whole thing is about thinking about what new processes, what new technology will bring to manufacturing, and how to be able to optimize and get maximum performance out of manufacturing systems if we have data, if we knew everything about what the machine was doing, everything about the execution, everything about the process, whether you're on process, whether you're still manufacturing to schedule, you're still making the right part, whether you have measured and created the right part, tolerances are all within spec. There's another area that we get into, things like this. So basically, as we're flowing all this information, which we're talking about, through the systems, we also have to make sure, from a security standpoint, that we trust all the data. So as we go out and we distribute manufacturing across multiple sites, and we start getting into local manufacturing. Has anybody heard about that? Some of the trends which are supposed to come out, which basically will allow manufacturing to occur locally. So instead of having to have these supply chains spread across the world, we can actually do distributed manufacturing, where I can manufacture a part anywhere in the world and basically have it come out the same way. That's one of the goals of a lot of these processes. Also, be able to have variability in the parts. So that instead of having to always manufacture the same shape or the same form, the same colors, and have a very finite set of choices, I can now have a broad choice. To be able to do that, we need to be able to trust the data that's coming out. If I'm a small shop someplace and I receive a design, I need to be able to trust who it came from. From the supplier's side, from the higher tier OEM, I need to be able to make sure that I know who it's going to and only that company has access to it. And they can only make so many of those parts. So I need to have certificates and signatures and everything. Even from the data that I collect off of the machines, I need to know that that data actually really did come from that machine. Because I could actually, one of the projects that Virginia Tech is working on is how to be able to spoof these various different documents, data, and so forth, similar to like what Stuxnet did. Stuxnet was a way to be able to spoof data coming off of machines to be able to compromise uranium enrichment. So certificates and signatures are very important. That gets down to provenance, which is basically making sure that whenever I get data or whenever I get a document from anywhere, I know where it came from and who generated it. Also, that the IP is being preserved as well. When you talk about digital rights, that is making sure that whoever gets access to it only has access to it for the purpose that they were intended. Similar to when you buy an ebook, only certain people can read that ebook. You can't just distribute it randomly. So there's also things around digital rights and digital media, which doesn't exist in manufacturing right now. So these are all areas that are going to need to be addressed from the design perspective. So I'm going to go a little bit into some basic concepts. I'm not sure. So I asked about this in the beginning. So people familiar with like lean concepts, Six Sigma? They teach it here? That's actually, yeah, interesting. Last place I was, they didn't talk about it too much. So big one is elimination of waste. Waste being any unnecessary process. So time, downtimes, maintenance, and so forth. In Mura, being able to make sure that your processes are executing smoothly. The flow is smooth throughout the entire manufacturing process. So to be able to really understand where your time is going, again, you need to get data from your system. A lot of this came out of Toyota and the Toyota production system, so talk a little bit more about how data drives it. Six Sigma, basically around quality. You have to understand how your processes are, how good your processes are at producing consistent, good parts. And Six Sigma comes from 6 standard deviations, and basically to be able to get into that 3.4 defects per million, which is the goal of Six Sigma, certain steps are necessary, and this will actually help with both of these things. The last one I'm going to go through is OEE. OEE is an equipment came up by the equipment builders to be able to make sure that the equipment was functioning correctly. So it was done by the machine tool builders, and there's a paper on it which comes out of AMT, which is actually really good about how to calculate OEE and best practices. And it's around 3 different pivotal ideas: quality, a metric for quality, how many parts are good versus total; performance, how fast is my actual production process compared to what I originally predicted it was going to be. And then availability, how much time is my machine actually producing versus the time it's scheduled to be producing. And along that line, if we think about the flow, so we think about a manufacturing process. This is a value stream map coming in. So we have the supply chain, supplier coming in with the raw material that goes into inventory. Then we have our processes. We have to understand things like the cycle time, the uptime, number of shifts, the amount of time each one of these processes takes, how much time it takes in between, and so forth, and how this flows. Now, if you look at some of the automotive systems, they don't really believe in inventory. It's basically single part flow all the way through, so it's just one part being passed station to station, flowing through the processes. And then how we schedule these processes. This is the way we do it right now with weekly and daily schedules for each one of the different machines. But again, as we start getting into some newer systems and we start getting a better handle on our data and what our machines are doing, we'll be able to get to systems where we can do this in near real time. We can start scheduling based on the performance of each one of these systems and do rapid changeover. These value stream maps are fairly static. We need to get to a more dynamic version of value streams. To be able to do that, we need to understand time. And I'm going to go a little bit through OEE now. And we understand, so this is basically understanding where time goes. And one of the important things you get from understanding how your machines are operating, if you can collect data from your machines, you can actually start to understand how each one of these buckets are being executed actually on the machine. So you can start, you have your plant schedules, you have your scheduled downtimes for the machines. Delay time, this is when you're waiting for parts or some process, upstream process. Repair time is your maintenance time, so that's unexpected. And then we get into our non-process times. Non-process times are times when you are doing things like setup, tear down, part changeover, to the point where we get into actually our process time. Our process time is a time we're trying to, this is our good time. This is the time we're actually making chips, executing a part program, doing value-added work. The idea is to try to reduce this time down as much as possible. So if we look at from our scheduled downtime, this is according to our schedule, this time here, these buckets from delay, repair, non-process, we're trying to reduce those as much as possible so we can maximize this and have the machine operational as much as possible. And if you're not collecting data, it is really hard to be able to optimize that time. So, this is a quote from Calvin. Basically, if you don't measure, you can't improve. And again, to go back to that number, only about 5% of shops right now are collecting data. And if you're not collecting the data, if you're not understanding what's really happening on your shop floor, it's almost impossible to really improve those systems effectively because you have to understand what the machines are doing, and you need to do it in near real time so you can react to problems that are occurring in the manufacturing and execution systems as they're happening. And this goes back to the small to medium manufacturers. But what are they worried about? Quality, on-time delivery, making sure their processes are consistent, executing correctly. They need operational visibility. And this is actually operational visibility goes up and down the supply chain. So if you think about it, a small to medium manufacturer, if they could report up how effectively they're executing upward, it may actually help them to increase the visibility of their processes and reduce the number of surprises if things are running behind or if they run into a manufacturing problem. They may be able to get the higher level whoever they're supplying to understand what's going on and make adjustments more proactively instead of waiting until it's too late. So actually information and visibility, this has happened actually in software too, where visibility actually helps to increase the effectiveness and the satisfaction of the people that you're supplying to. And the last one is basically, this is based on theory of constraints, which comes out of Goldratt. And I mean, the operative goal of almost every company is to make more money now and in the future. It's kind of an obvious one, but people often forget that. You know, the goal is to just keep improving and keep improving and keep growing. So now, what is MTConnect? Let's talk a little bit about it. So MTConnect itself is a way to get data from machines in a common format. So basically, we think about what machine tools are giving us as far as data. They're giving us a whole bunch of different things. This actually is sort of a pretty printed version of the standard, but you can understand things like, you know, whether it's an e-stop state, you can understand what block of code it's running, whether it's in automatic or manual mode, what line of code it's currently running, programs, feeds, speeds, positions. It gives you that raw data coming off the machine. It tells you exactly what it's doing at any point in time. And the big thing is that, you know, whether it's a new machine, an old machine, or different vendors, different builders, different controllers, the data is always the same, meaning that an X position is always going to be in millimeters, and it's always going to be called a linear X-axis, and it's always going to be in millimeters, and it's always going to be called a position, and we're going to know what the coordinate system is as well. So that consistency allows you, from an analytical perspective, to be able to take data from multiple different sources, multiple different types of equipment, and apply the same analytics to it and achieve results without having to reinterpret that data from every single source that you're going out to. And it's read-only because we didn't want to have any safety issues stopping us from deploying. So one of the big issues you have in manufacturing, and this is actually industrial internet if you think about it, the big difference between industrial and consumer in cyber-physical, if you want to also use that term, cyber-physical systems, is that cyber-physical systems have a safety issue. Whereas if you're merely just collecting data from, let's say, a sprinkler system or a health monitoring system, there's very little chance that that system is going to actually cause any damage or hurt anybody or have a safety issue. Industrial systems have safety issues. Basically, a machine tool, if for some reason it happens to start up when you're not expecting it, can kill somebody. It can rip an arm off. They're dangerous pieces of equipment. And because of that, we didn't want to get into the situation where somebody was going to be compromised, where safety of the machine is going to be compromised, so we made it read-only, meaning that you can't change the operational states of the machine. So it's a data pipe coming out. We used, at the time, the prevalent standards, HTTP and XML. In the next versions, we're going to be going over to things like JSON and MQTT, things along that line. But the deal is, with MTConnect, you can use any standard technologies and handle the data. So it's very easy from an application standpoint to be able to collect data from machines, process the data, and understand the semantic meaning of the data. And that's where the simplicity comes in. So are people familiar with various different manufacturing processes? MTConnect first focused on primarily milling and turning processes. We've recently got into things like wire EDM. There is a group that's now thinking about additive, and some of the machine tools now, some of the milling machines are now doing this hybrid additive. Heard about that? Where it's a little bit of both. Are people familiar here with wire EDM? Okay, great. Yeah, a couple. Yeah, sometimes people don't know too much about that, but it's something that we're getting into right now. And we also handle both CNCs and PLCs. So for milling and turning processes, we've integrated with most of the big controller and machine tool builders in this space. And we've also added, in a couple of cases, sensors. So the other thing that MTConnect provides sensor data, semantics, across a broad array of sensors. So we went into sensors, we found that there wasn't a good standard out there for collecting data from like even thermistors, vibration, acoustics. It actually surprised me when I found out that there were no standards out there which standardized the units and the vocabulary when talking about these things. So MTConnect actually took that on as one of its tasks to standardize sensor data. So one of the things you can do is actually hook up like an Arduino or a small sensor device and get data and pipe it through MTConnect. We've actually done it at up to like 8 kilohertz in XML, which is even more bizarre, but it works. And it's pretty effective. I can even show a demo at the end of this if everybody's interested. We handle motion, various different axes, rotary and linear motion. And we handle the translation from PLCs and CNCs to the common vocabulary. So when we talk about things like machine tool states and so forth, we handle all that. For wire EDM, one person heard of it, we're now working on standardizing the vocabulary around wire EDM processes. These are machines that take incredibly highly charged wires and cut through hard metals like titanium. And they're great for doing roughing operations where you want to be able to remove a lot of material. If you think about it like taking a hot wire and cutting through styrofoam, that's pretty much what wire EDM is, but for metal. And there's a couple different flavors of this. There's your wire where you're just dragging the wire through the piece of material. Some really complex geometries because you can actually twist the wire in various different ways. We're also working on sinker EDM and other EDM processes where you have an electrode even up to, I've heard, the size of a car bumper, which can basically plunge and remove huge amounts of material very quickly. We're going to be modeling high energy power sources and dielectrics, pumps and tanks and so forth. So all those types of systems and components are going to be modeled within MTConnect. So to look at sort of a high level of where MTConnect comes in, people familiar with any of these other standards? ISO 13399, QIF? Yeah, so ISO 13399 is a standard for cutting tool geometries. It's basically a document that will describe all the bits and pieces of a tool that you need to be able to assemble. ISA 95 is a process standard that tells you about all these processes to be able to make something. And QIF is a standard for quality information framework, comes out of Dimensional Metrology Standards Consortium. These are all documents, and they're domain models. Basically, they're information models that describe the vocabulary, the semantics around a particular type of concern. At the other end of the spectrum, you have things like OPC, Profinet, and Ethernet IP. These are standards that provide communication protocols and a little bit higher than your standard like Ethernet, which is just basically blobs of data. They provide syntax around it. They tell you like key value pairs and so forth. And that's where these guys fall in. MTConnect is kind of in the middle. We provide the semantics, the domain model, the vocabulary around each one of these different areas, as well as we also provide the transport. We just use HTTP. We actually can layer on top of these other standards, like we have an OPC UA companion specification where you can send MTConnect data through OPC if you want to. And use OPC UA if you want to use that as a transport. But then you're still using the MTConnect data model. We really focus on the data model. So if we had to give up one thing, we give up the communications layer and just focus on vocabulary. Because when you come down to it, the vocabulary is what really drives analytics. Being able to use that common terminology for every single piece of data you're getting off the machines gives you a huge boost when you're trying to figure out what does this data mean and then become predictive, proactive, and develop your applications. So the architecture of MTConnect is basically this. You have, go through it quickly, call native adapters. So on some machine tools, especially some of the newer machine tools, you'll have an adapter which sits right on the machine tool itself. So like on a Mazak or in Siemens controllers, the adapter will basically be embedded within the controller, and you'll run it on the controller itself. You can add additional sensors to that machine. Let's say you want to get coolant temperature, or you want to get vibration or acoustic signature off of one of the components. You can add additional sensors on that. The next is we have an older machine tool, let's say a 20-year-old machine, and we can do what's called a legacy adapter. A legacy adapter is basically a small software component which then usually hooks up to things like the 24-volt wires off the PLC and interprets various different binary signals on the machine to translate them into MTConnect vocabulary. The third is networked adapter. And the network adapter translates from whatever the proprietary network-based protocol like Focus 2, LSV2, there's a whole bunch of them out there, to the MTConnect vocabulary. Now that just is a first step. We're getting the data off the machine. The second is the agent. The agent provides the HTTP protocol and translates that data then into XML. So we have basically these translators from the machine's proprietary APIs or the machine's proprietary protocols into the MTConnect standard. And from an application standpoint, all I need to worry about is this one agent here. And the agent itself just speaks HTTP. It looks like any other web server to the rest of the network. So when you're interacting with MTConnect, you're just basically making HTTP calls and then getting data back, either streaming or otherwise. And it gets back into your application, and then you can run your analytics in your application. And again, it's read-only data flowing out of devices. You have your various different inputs. They all go to the agent. Now, one interesting idea about this is that we talk about sensor fusion here. And we're getting this binary data off of the machines, off of our sensors, and we're fusing it together. What we mean by that is basically MTConnect has this idea of timestamps, which is something everybody knows about and seems pretty obvious. But if you don't timestamp every single piece of data, you can't really reconstruct causality. So one thing that we do is we allow different data streams to be merged together and given a consistent timestamp. We do that in the agent. The agent can even do what's called relative time, where it can correct for clock drift. It can also have a millisecond offset and be able to then reconstruct the real time off of that. So every piece of data that you get has an existing timestamp associated with it that allows you to then figure out, when the machine was in this certain mode, this was the sensor data that I was collecting from it. So this was a temperature, this is a vibration, these were the loads on these different spindles, this was the position they were in, this was the spindle speed, feed rates, all the different data about that machine. Now I have sensor data coming out, and I know exactly when everything happened. And the timestamps also allow me to be able to collect data, and if I don't collect it every single millisecond, I can still reconstruct that entire chain of events and associate them together. So the first step is we get this data coming out. It's all fused together. And then first step is sort of a syntactic transformation. I talked about things like OPC, Ethernet IP, and control in various different protocols. That's where you're basically assigning a tag value. So the tag is some arbitrary name you give the data, and then the value is some value in some set of units that are probably local to the machine. And to be able to go to the next level, this gets you a certain step. And if you stop here, the problem is that even if you know what type of data is, I know this is an integer, I know this is a floating point number, this is a floating point number, I know this is an integer, I still don't know exactly what that data means. Right now, these are basically uninterpreted. A lot of the protocols that are out there right now stop at this point, at the syntax layer, like OPC stops and Ethernet IP stop at the syntax layer. You need to go to the next level, which is basically the semantics, where you have a model of how the information is associated with each other, basically the components of the machine, the linear axes, the rotary axes, and then the various different pieces of data that are associated with that, be it the angle, the rotary velocity, the positions, and then convert them into a common set of units. So here we have 5,196.54 millimeters. The load is 12.43. That's actually a percentage. We know this is now an RPM, and we know that 2 happens to be translated into an active state on the controller. So we need to translate it into this common vocabulary and then do interesting things with it. Once you do that, then you can start writing your applications, and you can start actually getting knowledge and information from the system. This is just raw data, pretty much. That's the whole value proposition. And as we start to bring data from various different systems together, and as we start to integrate it, the idea is that we're going to bring multiple different services. So if we look at, let's say, equipment manufacturers, this is the area that we're providing. MTConnect is really a service. If you think about it as an HTTP RESTful service where you make a request, you get data back, and you know what the data means. That's what this guy is here. Eventually, design systems and supervisory systems and engineering systems at different levels will also be providing services that we can then integrate these things together. And this is the first step of being able to get interoperability between multiple different systems. That's how we're going to be able to make, if you talk about, next industrial revolution, by interoperability and integration of data and services from the entire digital thread. That's how you get to that point. And that's how we can start to achieve some of these things like self-optimized and self-aware systems. So from the point of view of what we can do now, we're really talking about these continuous improvement processes. So we talked before about the idea that you're continually trying to improve your business and trying to make more money and so forth. And to be able to do that, you need data. So we really need to look at things like optimizing your execution processes and keep optimizing those. I mean, once you get to a certain level of productivity, you can always get more productivity out of it. You can always find better ways of doing things, improving your processes, and increasing your workforce training. MTConnect can actually be used in some ways for workforce training. If somebody is executing a process, they know how that process works. You can actually capture that process and then check to see if the process is still being executed in the same way as it was before. This is a big issue. Remember, we talked a little bit about distributed manufacturing. I want to be able to move a process from one location to another location. Well, we actually call it tribal knowledge capture, where I can then say, I'm going to capture how it's done over here, the exact steps and the exact feed speeds, tooling, all the information about how that process was executed, and then be able to replay it. There's actually an issue in a lot of SMEs that have been doing processes for many, many years. In that video, we heard that a lot of times you get your three-dimensional model, you then snap it down to a 2D drawing, and then you build your processes off of that. The problem is that then you're into sort of the paper realm. And a lot of what it takes to be able to get that part, after you go through the iterations and the prove out and so forth, to a stable state where you can make that a good part every time, a lot of that information about what it takes to actually do that is lost. Or it's in the head of the guy who's executing it. The operators are the guys who know how to do it, know how to make that perfect part. And that's great as long as they stay, as long as they don't retire, nothing happens to them, they don't get sick. But if that person or that set of individuals, if she doesn't come in or she gets sick or something, you're going to get into a knowledge gap, and you're going to have to rediscover how that process was done. So part of what you can do with collecting data is you can collect how processes are executed. This has benefits in being able to make sure that you can repeat a process, that you can train new people on how to execute that process, and also tell why first shift is 3 times more productive than third shift. What are they doing differently? Often it's not just because third shift is screwing around. Often it's because first shift has either been trained or there's some special trick that they know that the third shift doesn't know, and you need to capture that. So data can help you capture all that. Tooling optimization. We actually do tooling optimization where we crowdsource tooling data from sites and then find optimal tooling strategies. So you can do things like that. You can actually figure out what is the best way a tool can be used for a manufacturing process. You can predict quality, you can predict yield, things along that line, by being able to find what is highly correlated with a good part. If I'm checking tolerances, I'm checking my production processes at each step, I know where things are going wrong. Strategies of how to manufacture something, processes, etc., and then design for manufacturing. Looping back to engineering, basically I can say, okay, this is how execution, when I engineer something and I create a part program and a tool path that does this is how it is actually executed. This is the efficiency. Talk a little bit about that. There's a couple of research projects we can go over. The other place is going all the way back for design. In other words, if I design a feature in this way, this is the entire chain. This is how it's going to come out at the end. All the way through the engineering process, the tool paths and so forth, and then to the execution. So often in the engineering stage, there are a lot of assumptions made about how it's going to be executed and simulation and so forth, but often that doesn't actually come out right because the machines don't quite operate the way simulators operate, and things don't quite work the way they do in an idealized world. You know, physics and reality come into play. So we need to understand exactly how that translates, and by collecting data and analyzing data, we can actually get to the point that we can start to make predictive assessments of these things. And the other area, when we talk about process, is basically what we talk about more self-aware. I've come back to this a few times, of being able to redirect. So if I have a failure, we can work around failures. We can even go, if we want to, we can assess the trade-off between doing something externally or doing something internally. So if, let's say, I want to manufacture at another site, and that's actually going to be more efficient than if I try to do it locally, I can do that. I can make these assessments because I know the actuals. I know how things are actually going to play out in my manufacturing process. And that's where we start getting into what we were just talking about. You know, Industry 4.0, digital manufacturing, and predictive, and so forth. All these big words that everybody's talking, or big terms that everybody's talking about these days. That's how you're going to be able to achieve it. Another area that we've worked on within the standard is machine to machine and automation. And we have an interesting way of doing it. Is anybody here working on like robotics and process automation, things along that? Okay, kind of, good. At least, okay, see what you think about this. So one of the issues that we ran into, actually I'll jump forward a couple of slides and back it up later, but was the fact that most integration of systems started with sort of a 24-volt wire connecting two different machines together and working with PLCs. So this is actually from last year. This is a robot-ready option for a Haas controller. I mean, most controllers do it. Akuma and everybody else does it this way too. And basically, it's just a bunch of wires, and you have your different clamps, unclamps, cycle start, door open signals coming back and forth. So it's just pretty much about, what is that, 5 or 6 binary signals going back and forth between your machine and your robot or your cell controller. The problem is that this solution here, if we think about it, you have a cell controller, you have a bunch of PLCs which integrate the different systems together, custom interfaces all over the place, and you're dealing again with these sets of wires and this multi-level sort of binary signals going back and forth, and then some vendor applications there to be able to support the integration of these systems, and often they're just one-offs. They're pretty bespoke. If you look at most cell setups, they're pretty one-off type solutions. We were trying to get into a cheaper, simpler alternative. I did a project with NIST and Ross and NCDMM where we integrated machines and robots together using sort of a simple IT-based approach where we just connected through the network the device control, the machine tool and the robot, and created sort of an executive process which received real-time data, but highly semantic data about what these machines were doing. And basically the way it worked is we were just, each side was listening to the other side. So if we look, the machine tool listens to the robot, and the robot listens to the machine tool, and we spoke at a high, what I call semantic level. So instead of binary signals, we were talking about what the part was, and we're talking about the things like the robot didn't say move, or the machine didn't say, robot, you move to this position and get this, pick up this piece of material. What it said, the machine tool just said, I need a piece of material. I need something to do. I'm ready to accept material. So there's a interface that we created called material load, and if the machine tool says it's active, it's waiting for something to be able to fulfill that need. A robot, or it could be anything, really. And then the robot then says, okay, I've taken your task and I'm executing your task. And then the robot asks the machine tool to do things like open its door. And the machine tool then says, okay, my door is now open. And it says, okay, I need you to close your chuck because it knows the machine tool needs to hold the material. And then it waits for that to be done. Then it knows it can release and retract. And then it tells the machine tool, okay, now it's okay for you to close your door. These are just requests that are coming back and forth. It's not actually telling it, it's just saying, requesting that you do this, and so we can get a complete operation. The idea is when we elevated everything up to that higher level semantic, we found that was actually pushing the intelligence out to the edge devices. So instead of having a centralized control system, which is trying to orchestrate all the behavior of all these different systems, we had each system kind of taking care of itself and knowing what it needs to do. And by distributing this intelligence to each of the edge devices, we found that we had better resilience and no single point of failure. And we also had a dynamic system where we could change over parts. Instead of communicating just a single byte, now the robot was saying, I picked up this type of part. I know the part ID. And the machine tool can say, okay, and especially with the new stuff that we're coming out with in our parts addition to MTConnect, the machine tool can say, okay, I know what part program I need to run for that part. I know what the processes were before me and after me. I know all this information about this part. So it has this rich information model now about the process it's about to execute. And the machine tools are able to make intelligent decisions, and the robots are able to make intelligent decisions, and basically you get this next step of dynamic flow. So that's another area that MTConnect has dealt with, this idea of dynamically connecting devices together and having them communicate, but at a higher semantic level. I found out that we weren't actually the first ones to do this. It was done, I think, at MIT back in the 80s. But the computational power necessary to be able to run, just coordinate the messaging was not there, and the networking wasn't there. And the cost saving was huge. So if you look at the advantages to the SME or the manufacturer, we got rid of all the PLCs. We got rid of all that, the additional equipment. We were able to get to just a couple of applications running on either side. Yeah, so the question was, does the machine need specialized sensors and other equipment to be able to interoperate? And the idea of this was, yeah, right now there are special requirements because the machines don't come with it at this time. We're starting. I mean, the idea of the standards and the reason you create open free standards is so that you can get machine tool builders to then implement. So, let's say if you bought a new Mazak or a Kuma or, Mori type machine or any machine like Haas or whatever, and it came with this interface ability built into it, we were trying to get to plug and play. So I'd be able to plug in my robot to that machine, and it would just be able to communicate. Well, we have a project going on to actually prove out some of this, where machines will be discoverable. Location will be discoverable as well, where the machines will be able to communicate their capabilities, and you'll be able to understand where they are and what they're capable of doing. And then you won't need special technology. Basically, even with things like, let's say, take a universal robot, which you can then put without an enclosure, and if you could just park that in front of a machine. I know a couple of shops that are doing this, but it's very simplistic process right now because things like the robot actually has to push the cycle start button to get the cycle going because a machine doesn't have an easy way to be able to integrate that information. So the next step forward in automation is really to be able to first off, raise it up to a level where you're not dealing with individual sensor signals, where you're dealing with higher level semantics and able to communicate the entire manufacturing process. And then the next level, to be able to get the devices to the point where they can discover each other, and then you can get into plug and play. So that's where we're going with this. Actually, I might just skip over this. This was a little thing that I did. But that's just a little video that I made a long time ago about integrating it together.
The system's architecture used MTConnect ROS industrial demonstration. At NIST made use of the MTConnect read-only communication strategy, where devices do not directly control each other. They publish their state using an HTTP server, and the other devices perform actions if they are capable to do so. In the demonstration, we use a robot and a machine tool. The machine tool does not send messages to the robot. The machine tool requests data from the robot, and the robot from the machine tool. For example, when the robot changes its open door state to active, the machine tool responds by transitioning its open door state to active. Once the door is open, the machine transitions to complete, and the robot acknowledges by transitioning back to ready. The roles are reversed when the machine tool makes its load material request from the robot. This is peer-to-peer communication. The benefits of this architecture are the ability to scale from a single device to multiple devices, even different types of devices. When the new devices are added, the communication between devices is identical to the one-to-one scenario. This architecture easily extends support of many-to-many communications, which enables fault-tolerant processes that are driven by demand and availability, not a preset sequence of operations.
Yeah, so it's kind of a high level of what it is. So basically, we proved this out actually at NIST and had incredibly good results as far as resilience and the ability to have the processes self-recover. So when something went wrong, pretty much just picked up where it left off. And the machines, because the robot wasn't dependent on just a very narrow view of the signals, it could tell what's happening on the machine tool. They were reporting their entire state. We were able to make intelligent decisions about how to recover the process and how to carry on. And that sort of edge-level intelligence, we're able to push more of the intelligence to make these devices more intelligent, get away from the single-wire solutions, will, I think, bring in a new set of, a new era of automation. That's my hope, anyway. So I'm going to go through a couple of research projects. These were actually done at various universities around the world, and this one's over at UC Berkeley. Give some ideas of some things that people are working on right now, and I'll talk through some others that are going on. So this is actually by Ronak, and he did some predictions using machine learning on manufacturing processes, basically efficiency and so forth. And he's working at the LMAS. He's doing his PhD at LMAS, which is the sustainability group over at UC Berkeley. So a lot of it's around energy and energy efficiency of different machining strategies. And pretty much what we talked about, he did. So he took process parameters, took them into the machine tool, added additional sensors in. Again, we talked about sensor fusion. Pumped that into the MTConnect agent, and then processed all that, and then developed processes to extract knowledge from the manufacturing data and then feedback. So this is just like an optimization feedback loop that he created, going from the data coming out the machine, the sensors, gluing it together, and then improving the process. And the hardware was pretty simple. Basically, just take Data Moriseki. This is a little mill, micro mill, with a FANUC controller, and he added a high-speed power meter. This gets you 100 hertz power sample data. If you're interested in getting any of this type of kit, I can also try to hook you up with some pieces of equipment that, some sensors and other things. We have a few different options that, we can give away. Then he popped it into a switch, and then that was aggregated in an MTConnect agent. MTConnect agents can aggregate data from multiple devices, so you can have, we've even had like 50 different machines hooked up to the same agent. The agent, again, is that protocol server, so that's your point of contact for getting information from machines. And so we had the data from these different areas collected up, and this is your controller data. So speeds, feeds, loads, the actual code that was being executed, so we know the block and line of code that's being executed. And we know how much power was coming off of the 3 phases coming into the machine. And he did this condensation and then simulation. So it was a 2-phase approach. So he's basically trying to collect data and then simulate based on what he collected. And then you're able to take that data in for higher levels of data. So if you talk about pipeline, after you go from semantics, you then go to what we call enrichment, where you take the data that's coming out of the semantic model and you start to derive additional meaning to that data at a higher level. So things like depth of cut, toolpath strategy, cutting strategies, volume of material removed, and so forth. This doesn't come from your machine doesn't know how much material it's removing, it doesn't know how fast it's removing it. It just knows what it's doing. It's doing the motion and everything else, and the positions that it's at. And by using and combining it with your process data, you're then able to come up with higher level abstractions, and that's what that is. So that's, what we call sort of an enrichment, where you take it and get to the higher level of knowledge and assessment. So then, again, went through this whole pipeline. Then you could do simulation, so you could make changes and then simulate what those would do and compile it and then create these models. And these are higher dimensional models. So basically he was going through this whole process of modeling based on what he was observing. And this is getting a bit too deep for me, and you can actually ask him. He's a great guy. He wrote UC Berkeley about how this actually worked. He wrote a paper on it. But he was looking at these different dimensions, basically your spindle speed, feed rates, direction of cut, cutting strategy, length of cut, and so forth. These are all the different attributes he was taking into consideration. And then he was looking at the energy used for each of these different strategies and trying to optimize around that to predict the characteristics. And this is the sample part that he used. And some of the different, he has test parts and various different strategies. And again, so taking a look at these different strategies of cutting and toolpaths, his objective was to be able to predict how well these different strategies would work by being able to observe how they worked in the actual energy profiles. Because when you're going at it from a purely sort of first principles model, often things don't match up when you actually go to a machine tool. And by actually testing this thing on the machine tool, he was able to tell, it's not just around speeds and feeds, it's about, there's a whole bunch of other motion and various other loads and so forth that take place, and some of the physics, and basically he was able to optimize a model around that to find an optimal energy efficient toolpath for pocketing. So anyway, that's one of the projects that was done with MTConnect. And again, using MTConnect and being able to fuse the high-speed sensor data with the machine tool states, the blocks, and every execution states of the machine, he was able to then pair everything up and know exactly what operations were taking how much energy to be able to do this analysis. So this is actually done at IIT Madras, and we have an office over in Chennai. So this is one of the projects that we do over there. And this is actually an interesting, the idea here was to reverse engineer a machine tool from some base principles, but use real data collected to be able to do it. So they built a machine which was just basically a load and a generator. I'll have a picture of it in a second. And then collected 100 hertz data again from a high-speed power meter, and then put it into a simulator and was able to simulate pretty accurately the machine tool behavior. So this is the rig they came up with. It was basically a 3-phase AC motor with a coupler and a DC generator, which would put a load on it, and then a relay bank, which was pretty much just a whole bunch of these huge relays that they stuck together. Did a nice job of heating up the room as well. And then a load bank that was controlled by an Arduino, which would then switch various resistors on and off to simulate different load patterns to be able to simulate a real manufacturing process. And then also adjusted the power going into the motor to be able to simulate speeds and the speed of the either the axes or the spindle. I mean, of course, manufacturing, metal cutting, you have to really focus on spindle speeds. And that little microcontroller here was just an Arduino. So a pretty simple, cheap kit. And then the simulated data would be the data that was pumped into the system so that we could simulate the behavior of the machine. So one of the first things they found out was how fast you needed to sample. So it was like, how fast is good enough? And they tried at 1 hertz, 10 hertz, and then 100 hertz, and found that with 100 hertz, they were able to get a fairly good fit of the spikes. The problem is that if you don't sample fast enough, you lose a lot of this detail. So you lose these spikes. Even at 10 hertz, you're losing a lot of detail here. And that can lead to erroneous assumptions about the way the behavior is going to occur. So they also were collecting data from real machine tools. So at the same time, they were sort of setting up this rig, they were collecting data and running these processes on machine tools, and then looking at recurring machining cycles. So this is a single set of operations, spin up, spin down. So we look at the way this we look at sort of in a broken down form. This is your machine startup time right here, and then you spin everything up, and then you're ready for operation. This is when you start your spindle, that time right there, and then your acceleration, your main accel, and then this is motion to get to that point, and then this is when you actually start removing material, back down, and this is your power down, your spin down, and so forth, and machine off. So these were the fixed power. This is the operational power, meaning this is the amount of energy it takes to be able to spin the spindle, and this is the amount of tooltip power. They said this is, I guess, based on simulation and theory, how much power it actually takes, and I guess the unproductive power is the delta between those two. And then they looked at a real machine tool and said, hey, let's try to find features. And let's be able to identify features by just looking at the power data coming off the machine. And that's where these things were. So they found these different patterns to be able to find the feature sets within the data. And they could see the motor start, the load levels as the cutting depth increased. Rapids exhibited this type of pattern where you had these nice little spiky bits coming out. So, low level operational power, but spikes. And these are your cutting powers. Fun part was when they actually started comparing it. This is their simulated on their simulator after they were able to collect all this information. And the actual, they were actually able to get within very, very close to the actual. So here's your actual simulated. This is what they did off of their rig by basically reverse engineering the machine and building a model for those different power levels, and then putting it back into the feature sets and understanding how those features exhibited various different loads and speed changes. And basically, these were the two fits, and they got pretty damn close. So again, that was taking data coming off a machine and understanding what it was doing, and then looking at just power data coming off of it, being able to fit it, and then reversing it out and simulate it. The next step of this is basically, now I don't know what the process is. Can I come up with just a simulation of any machine tool out there? So I can create basically an N-axis machine with various levels of complexity, but I know the basic behavior of that machine. Can I simulate that from base principles? And that's where they're going. And so, I mean, that's the basic idea behind this. So you can do that once you understand the data and you understand processes and understand what's happening. The other one that was interesting, we did a 3D printing project out there where they were trying to find out, this is just a simple little, cheap 3D printer, plastic printer. And the idea was, what is most highly correlated to quality and strength? So you think about it in 3D printing. Now, this is used MTConnect as well. We don't directly support 3D printers today, but MTConnect is extensible, meaning that you can add additional data items to it if they don't already exist, and that's what they did. So they need to add a couple for 3D printers. But the idea, again, was sensor fusion, taking data from the sensors and motion and so forth, which is actually very similar to machine tools, and being able to apply it. So they did a series of experiments, and they used off-the-shelf software, open source slicer software, and reviewed literature and so forth, and then took a look at a number of different parameters for dimensional accuracy. Temperature, PID values, slicing, various different things. I'll go through them right now. And they worked on, there were 7 variables associated that they looked at. And they built this little cube here to do the testing. And they used just a simple vernier caliper to do the testing with 10 micron accuracy. And they also used a tensile strength tester to be able to make sure that the to test the strength of the part. And what they were looking for was from things like extruder temperature, infill patterns, and various other things like slice height and density, what was most highly correlated with the strength and quality of this part. And again, I could put you in touch with these people. They found that there were some variables that had very high significance. So for accuracy, this is the accuracy analysis. Let's see, I'm just going over this, sorry. The X and Y axes had opposing importance, and I'm not quite sure. They say the intercept had high significance. So basically they found that certain things were highly correlated to the accuracy. And I think temperature was also, so slice height was a strong predictor of the tensile strength, but had little significance for modulus, and infill density had, was a predictor of modulus, but not too much of tensile strength. So there were some things here that were kind of expected and some things that were unexpected, as well as temperature was modulus, but didn't really seem to have a big predictor for tensile strength. So there's more information on that out there. Anyway, I can point you at it if you're interested in that project. But anyway, it can be used for interesting 3D printing projects as well. There's some other work going on in that space as well. So that's most of it for the first part of this thing. You can go into the standard itself if you're interested. You want me to go dig deeper? Basically, from the standard itself, we have 4 information models. We have what we call devices, which is a model of the manufacturing equipment itself. It's what's called a logical model. And streaming data that comes out. This is time series values, time-stamped, which describe each one of the data items you can get from each one of the components and the data about it. We have assets, which provide a key value pair of data. That's for things like tooling data and for processes, and then just some protocol errors. So does everybody know a little bit about XML? A little bit? Okay, so the reason we chose XML at the time, it was first off the prevalent standard for standards. And it's very easily extensible. It also has verification built into it. So you have standards like schema, which allow you to be able to validate that it's correct, and it's fairly human readable. We've actually made MTConnect as readable as possible by sticking to some basic principles for naming of elements and attributes where they have to actually have spelled out words. We only have a couple of abbreviations for them. And we do use schema so you can do full validation, and we also use XPath to be able to express the, to be able to focus on certain aspects of it. So I'm going to go quickly through this. Basically, you have elements and attributes. Elements can have sub-elements, and they can be nested. An attribute is basically a key value pair within an element. So it allows for an association. It's basically some additional information around the element. And then there's data within the elements, like CData. If you look at HTML web pages, it's actually an XML document. Or you can have more nested elements, or you can even have mixed content. Like in HTML, you have CData, text, and then elements, and then more text. And each element needs to be closed with a closed element. So if you notice, there's an open, and then there's a closed. There are some shorthand versions of that where you just have, like, this is a simple element with just a slash at the end. It just stops you from having to put a closed element when there's nothing inside. All of our elements are in camel case, meaning the first letter of each word is capitalized and they're put together. Attributes are called snake case, where the first letter is lowercase and each of the words are capitalized and they're glued together. And the values are all uppercase with underscores in between. Just makes it consistent, and whenever you look at it, you know what you're looking at, and you know what the patterns are. We also have this idea of grouping, like in devices, components, data items, etc. Pluralized words are usually used as grouping elements. So just some basic rules. When you look at the standard, it gives you sort of a high-level idea of what's going on. And with XPath, we can then select various different pieces of the document. This allows us to focus on, let's say, one component. I can say, give me all the data just for the controller, or give me all the data just for the axes. And by wildcarding it, and these are based on attributes, so whatever at living based on this guy right there. So devices. This is called a probe request. And devices provide the logical structure. So it's each one of the components in a hierarchy. And the component's names, the element name describes a component, like axes or linear, rotary, controller, path, etc. And we provide the data items that go into that. So each of the data items has a certain syntax, a certain set of units, and that the units are always the same. So we've normalized all the units. And you can nest the components to be able to give additional structure to your device. And this model, what we call devices model, is MTConnect devices as a root element, only has this meta information. It doesn't contain any data, just information about what the data is. So if you look at a device, it's basically broken down this way. You have a device has availability and emergency stopper usually at the top level. Then you have a set of axes. And then you have controller, and the controller has a path. And the path will have things like program execution, controller modes, blocks, and path position with free space position. Yeah?
Does it only support 4 axes?
No, it supports N. You can have any number or combination of these. So you can have linear and rotaries, and you could do a robot with a series of rotary axes joints. We don't support a full kinematic model. We're waiting for another standard to actually give us a kinematic model. We also support things like systems, so electrical, hydraulic, pneumatic systems, and we're getting into things even like
Do
accessories, robot loaders, like small loaders or built-in components.
you think it
Yeah.
support anything more than values usage data, like point clouds and things like that?
Well, point cloud is made up of a series of time series points, effectively, right? So let's say you were trying to collect the path position and use that as a 3-space position as a tool, as the spindle or the tool traverse the part. You could use that tool to position to be able to construct a point cloud, and we've actually done this to understand every single point that tool traversed and reconstruct the shape of the part.
Well, I'm talking about depth camera data. So
We don't have camera data yet.
Okay.
It's something you could actually extend out to if you wanted to.
Okay.
No, we haven't gone into imaging or anything like that. This is what it actually looks like. So you have your devices, there's a protocol header, and your data items, and your axes, and so forth. One point on that. So the idea here was mainly streaming data. So point cloud data, files, and other types of information models, we're looking at more sort of in the asset space than in this space. So this space is primarily, this is data that's going to be streamed out real time from their processes. So each one of these data items will be given as it changes. So we do what's called delta compression. We'll talk about that in a second with some of the streams information. But if the data doesn't change, we don't write it out. So every 100 milliseconds, we don't push out the same data each time. If the value hasn't changed, we don't communicate. Every document has to have a top-level element. So in this case, we have a streams element. And if you look at the document, basically, there's only one top-level document element per document. And here, like at the component level, we have an ID, a name, and a UUID. And these are the component types, are the names right there, just to go through it. And again, this is a streams doc, and basically the schema location is for used for validation. And you can actually create your own schemas if you want to do extend the schema out. A data item is made up of all these different things. So basically, these are all the attributes, possible attributes of a data item. You have category. The ones that are required are ID, category, type, and that's it. For the sample types, you have to have a units as well.
What would be an example?
An example is right here. Let's take a sample, which is actually should be rotary velocity, and it's in revolutions per minute. And this is an extended example. This is a motion event. An event is just it's usually some kind of control vocabulary, like a state, describes the state of the machine. And then this is an emergency stop, which is also an event. And we express alarms as conditions. And I have a little more on that in a second.
Sorry.
Yes, Rico?
Do you store all of these documents just for logging, or do you actually process them, analyze them for some sort of future information?
Yeah, they're pretty much, we pull the data to be able to analyze it. So this is actually a real-time data stream coming from the machine.
So it's huge, right?
Oh, yeah.
So how do you handle that?
Well, that's a wonder of things like AWS and Azure.
So you use a Spark and Big Data?
Yeah. I mean, other companies don't store everything. We happen to store everything. You can, let's say you just want to get a couple of things from the data stream. Let's say you just want to look at, let's say, controller mode and execution state. Controller mode describes what the machine is doing right now. The controller state is like automatic, manual data input. One of these basic modes that are on almost all machine tools out there. Execution tells you whether it's actively executing a part program, ready, meaning it's not doing anything, just waiting, but it's ready to operate. Interrupted means that it's been stopped in the middle of a process, or stopped, which means that it was, well, interrupted means that somebody interrupted it. Stopped meaning that it actually has hit a stop for some reason. There's also optional stop, a couple of others. So those are your execution states and your controller mode. By execution state and controller mode, you can actually do most OEE analytics just by 2 data items. If you want to get a little bit more analytical about it, let's say determine when your spindle time, then you can look at things like your rotary velocity of your spindles and say, okay, when the spindle is spinning, and if you want to even get more analytical about it, you could drop down and say, okay, when the spindle is spinning and the load is over 10%, then I'm actually making chips. So by analyzing the data, you can get more and more detail about what's happening in your process. But again, yeah, it is all just streaming out at you in pretty much real time. We have these 3 different types of data items in the categories. They're event, sample, and condition. The event, again, are states. And they tell you things like the line number being executed, the state of the controller, the execution state of the machine, various different things like that. So if we look at it, it will only change whenever something changes. So in other words, whenever you'll only get an event coming out of the stream when it actually changes. You won't get it every single time. You can ask for the current value of it, but it won't keep telling you that you're still in automatic all the time. The only exception to that is something like a discrete event. And discrete events we added recently because of counts and messages. If you want to say, I'm making one part, I made one part, I've made one part, before, because we only supported deltas, you couldn't say that. Now you can say I have a discrete part count, which says I've just made one part. And the other problem we had was things like messages, where you get like a message saying door open, door open, door open, door open. Because we had to compress the changes, if you had that door open message coming out 30 times, you'd only get one of them. A bit of a problem. So we compressed it down. So that's an example of part count with a representation called discrete. And a standard event is something like controller mode. So the name is mode, category is event, and the type is controller mode. Second type is samples. So samples are continuous variables, things like positions, temperatures, so forth. They always have units. And like this is a path feed rate. It's actually I got this wrong. This isn't supposed to be millimeter per second squared or cube. It's oh sorry, yeah, no, this is correct. Millimeters per second path feed rate. This is a surface feed of the machine. You can provide optionally the native units, which in this case are foot minutes. And you can say, well, this is how the machine is reporting it, and this is actually, these are the standardized units. Every sample type has an agreed upon set of units. So we always have those in the same way. Similar to like you can have a sample which is in the units decibel. There's a time series and a type is displacement. And a sample rate is 44 kilohertz. Time series are where you can actually give out a number of sampled values in one go. So the problem that you run into is if you have to keep repeating a lot of the information every single time, the data stream just gets to be too big. Even for XML, XML is already a lot of overhead. Now there's a huge amount of overhead. So with time series, I'm able to compress that up a bit. We've actually been able to handle like 8 kilohertz data without a problem. Again, it's just numbers separated by spaces. But it works pretty nicely. And if you compress it up, it actually is not too bad. The high-speed power meter data, the 100 hertz data, is all time series. So it's in 10 chunks of 10. So 10 bursts of 10 samples. MTConnect batches things up as well. The last one is condition. And condition tells you what the condition is of a certain type of, usually around a component. So we didn't model alarms. Originally we had alarms in the system and we got rid of alarms and went over to condition because it was actually more descriptive. An alarm we found didn't tell you what was really going on. So we said there are 3 states a condition can be in: normal, warning, and fault. Normal being defined as everything is fine, no problem. Warning that this thing may need to be looked at, but right now it's okay and it may resolve itself. Fault meaning that it needs manual intervention to be able to correct this problem. So those are our 3 states. And if you have something, let's say you have a condition on temperature, you could actually have a sample that tells you the real temperatures here, and then a temperature condition, and the condition will be normal, let's say over a certain threshold, then it goes into a warning, and then over another threshold it goes into a fault. You can then describe all those using these 2 data items. And they will be contextualized. One thing they have to remember with MTConnect, these samples, these data items are contextualized within a component. So if I have a linear x-axis, that'll be the temperature of the linear x-axis. Now we're actually getting into a further level of decomposition in the next version. And we're going to be able to break these things down into things like the motor, the amplifier, and so forth. And that's not out yet. That'll be in the next version of the standard. So all this data that is described now in the devices model, that's your description of what you can get out of each component, is then provided through the MTConnect streams. And that's what this data model is here. And it provides real-time streaming data. And we try to sort of reach a balance between how much referential information you get, so that how much of the stuff that we repeated out of the devices model, and we put in here just so you know what we were talking about when we looked at the streams. And the streams is a flattening of the model. So if you think about the devices information model, it's hierarchical. You have nested components, axes and linear x, y, z. You can have components nested within that. Within the controller, you can have multiple different paths, so you can support multi-path machines or multitasking machines. So that's all supported within the model. But when you're streaming it out, it's inefficient to have to reconstruct that entire hierarchy. So what we do is we flatten it out, and you have these component streams which come out. And they tell you what the component is and what the name of that component is, as well as the ID of that component. And then you have the samples and events, let's say, and they're just listed in a long series. So basically, we batch them all up. There's 2 primary calls in a to get this samples document. This is what we call current, which gives you the current state, basically the latest value known to the agent of every single data item. And you can even say, give me the current value at a certain point in history. You can go roll back in time if you want to, within the buffer that MTConnect provides. So basically, you can configure the agent. Some agents have, up to like 100,000 or a couple of million events that they store. That gives you, let's say, a day's history in the agent. The agent happens to be it's a store and forward agent. So it's basically, if you think about protocols like DDS and MQTT, things like that, that's pretty much what it does. It gives you this pub-sub type framework to be able to capture data in near real time and also be able to recover from, let's say, a network outage. You can, if the network goes out, you can always recover exactly where you left off by picking up the sequence numbers. So the sample gives you then a time series of data from a certain point, either from the beginning of the buffer or you can say from a certain point. The data looks like this. This is actually a current, so we have various different things like here. I wish I updated this with spindle speed, but you have things like rotary mode. Condition is in normal state. You have path feed rates. These are multiple path feed rates, and you can see this is feed rate override, and this is your feed rate. So it's one value. Current gives you a single value for each one of these things. The header of this here tells you who sent it, the instance ID. That's the instance of the agent. If the agent fails and recovers, you can tell when that happens by looking at the instance ID. Buffer size tells you how much information you can store and has in its buffer. This is 131,000, which is the default number of data of events. And the sequence numbers. Next sequence is the most important. This tells you the beginning of the buffer. This is the end of the buffer. This is the current point that you're at. And if you look at that next sequence number, you know exactly where to start when you want to start pulling data out of the agent. And when we start streaming, we can have multiple device streams, one for each of the devices. So if you have, let's say, 30 different machines, you can actually cover them within one device, one streams document. So in other words, you request a current, it gives you current across everything in the machine. And you can see it's named here. This has a universal unique ID as well as a name. And we'll start going through the component streams. Now, there are three sections to this document. There's the events, the samples, and the condition area. Events and samples list out each one of the events and samples. Condition, we could have multiple conditions for a single type. So this is an example here, the component stream. The controller mode of the data item then gets translated to this controller mode here. This is just a little bit of mapping. So basically, we go from the controller mode here to the controller. The names, again, of attributes are always capitalized and underscored. But when they're put into the element, they're put into camel case again. This is, again, execution type. And events, we can't have, as I said, it's delta compressed, so you can't have two repeated events. They have to go and indicate a change of state. This is an example of a controller mode where you're going from automatic manual to manual data input, except for discrete, of course. And so discrete, you can actually have repeated values. And I just gave those two examples before. The interesting thing here, let me just go through this quickly. For things like path feed rates and other streaming data that changes very quickly, you'll notice in many cases that there's basically every 10 milliseconds or so, I think this is about sampling at that frequency, you'll get another line. So what we do is we batch up all the changes into a single document. That means that every single change doesn't have to be another network request. One request will give you a chunk of data. So we can actually, we're fairly efficient. And the time sequence, so this is the time series we were just talking about. And time series, basically looks like this, where you have spaced limited data. And the timestamp is always at the last sample. So if we have 4 samples here, this timestamp will always be the last. Then you can back calculate the beginning of the time series by taking the sample count and the divided by the sample rate, and that'll give you your delta. And another example was stats. So we also have statistics. Statistics work similar. So the sample comes at the end, then you can back calculate the duration of from the sample. We can have averages and so forth. So basically, data items can represent a lot of different types of data that you're going to get off of the machine. And you can basically build the model based on what you require for your sensors. Conditions, again, are normal, warning, and fault. Went through that briefly. And this is an example. So you can say when it's overload, load is high, so forth. They're usually unique by this native code, which is usually the internal code within the controller itself. Interesting thing about conditions, usually you'll only have one value per type within a sample at a certain time. So in other words, an axis can't be in the same position at the same time. Axis cannot be in 2 different positions at the same time. It's physically impossible. A machine can't be in 2 states at the same time. At different times. Yeah?
What about a machine with multiple tools?
Different paths. So you'll break it up into separate components, and each component will have its own path and tool information, path position, so forth. That's going to be your different heads and so forth. So that's modeled where each one has controller states, because it can be each running a separate, they usually will be running a separate program. And they will usually be running with different tooling and different feeds and speeds and other parameters. So all that's captured within the path component of the controller for multitasking. So at the same time, each component can only be in a single state. Makes sense. Except for conditions. So you can have actually multiple alarms that are going off for the same type of alarm. And that's where this is going to occur. You have this like with motion programs with multiple syntax errors. You can actually have them listed out here. So you can have multiple faults associated with the same condition. And everything needs to support this concept of unavailability. So every data item has unavailable as a value, regardless of whether it's numeric or text-based. And the unavailable for our condition just is unavailable like that. And there's only one requirement in MTConnect, and that's this. You have an available data item. The machine only needs to be able to say whether it can produce data or not. That's it. Everything else is optional. Of course, it's pretty useless, but at the same time, it allows us to model almost any piece of equipment or any sensor that's out there. If you required, let's say, a controller for every device, that meant that devices without a controller would not be valid. So we do it that way. We have cutting tools, and we're now getting into parts and inspection. Eventually, we're going to get into work holding. These are assets. Assets provide an entire information model about a certain thing. And the idea is that there are 2 primary concerns we found when we started modeling machine tools and data and so forth. The first concern was streaming data, real-time data coming off the machine. The second one was data models and information models about certain aspects of the manufacturing process, whether it's a part or a cutting tool or something that's used within the manufacturing process. So assets were the second thing we added, which is basically to have a key value store where we can then associate an information model with a unique identifier. And they're actually going a lot further with this, with targets and other things in the next version, where you can say this asset is for a certain set of devices. It's coming up in the next version. So with like a cutting tool, we have, this is the one that we modeled in 1.2. We have things like the cutter status, which tells you whether it's new or used or how long it's been, or whether it's broken. And we have process values like spindle speeds and feed rates and what type of connector it has, as well as measurements like the diameters, lengths, and functional lengths of each of the cutting items, each of the different inserts. That's what all this is about. And we can model all these different types of cutting tools. We use a similar semantic to ISO 13399 for the different codes, like these different codes here. And we can model things like step drills, but we deal with the use phase of the asset, so basically of the cutting tool. Other standards don't deal with that. They just deal with the model, the geometric model of the cutting tool. We deal with how is this tool going to be used, and as it's used, how does it get worn? How does it change? How do the measurements change? So that's where we go with this thing. That's what it's so special about MTConnect versus some of the other standards that are out there right now. And for that, we have these two different models. We have the archetype, which is kind of your template that says this is the nominal min and max of each of these different measurements, and then we have the actual measurements that are coming off, which is the instance of it, which is each of the builds. Each of the individual cutting tools that are actually used in the process, we provide as an instance. And this is what the actual data model looks like. So if the top level is a cutting tool, and then cutting tool life cycle tells you about this, how this exists in the manufacturing process. We have things like the measured value of the body diameter, protruding length. Again, everything is spelled out. It's all human readable. And that refers to this type of diagram with the codes here, so you can actually match from a 13399 document directly down to it. This is an archetype. The only difference is we don't have measured values because everything is just min and max and nominals. That's a big difference. And these are expected values. We can even put into it a full step model if we wanted to, in express format. Thing is, whenever assets change, we get asset changed events. Whenever they're removed, we get removed events. This allows us to track the assets in real time. So we have this real-time streaming model already, which is nice. Great. And we utilize that with the asset model to be able to push changes as they occur. So you always know what's happening in your machine. As assets are used, like cutting tool is used and it changes, it pushes out here through, again, that streams document. And we're going to get into parts. Actually, we're very far along. We're actually writing this up right now. So if you're thinking about interesting ideas, we're going to be supporting a full process flow model in MTConnect. I can send you more information on that if you're interested. This will go down to micro-planning. So it's each of the process steps at each one of the machines, all the way down to the activities and the constraints on those activities, feed, speeds, tooling. Anything that we can constrain within sensor data can be expressed within that model. So you can basically say, this is how I expect this process to be executed. You can give multiple routings as well. It's not just a single path through manufacturing. It can be multiple different routings, multiple options. We can express that all within MTConnect. That's the archetype, again, the template. The instance gives you how that process was actually executed, all the process events and activity events that occurred that are significant during the manufacturing process. So what we've done is we've basically given a data model for the entire digital thread for capturing everything that happened in manufacturing. And next areas that we're going to get into are things like in-process inspection is one that we're working on. So if you're thinking about ideas around measurement and tolerances and so forth, that's an area that we're going to be modeling fairly soon. And you can actually add new asset types as well. So if you have a special asset type that you want to put into MTConnect, you can do it. And it's actually very easy to do. Again, extending schema. Nice thing about MT. And these are just all the errors. I mean, it's just a standard set of protocol error set. And that's most of it. You can create new data item types by just putting them in there. New component types by adding them in again. And the agent itself will recognize and be able to extend. So if you put a new data item in there with a new name, it'll automatically do the conversions for you and make everything work nicely. So what I want to get into, sort of wrap things up, maybe take a couple of questions at the end, is the open source solutions that are out there. So there's already a lot of tools out there. So you want to start with MTConnect and play around with it. There is a GitHub site, github.com/MTConnect. Is everybody familiar with GitHub? Okay, a couple of people. GitHub is a great repository and a great version control system for software development. Distributed software development came out of Linux. Don't go into the history of that. But it is truly wonderful. And GitHub is one of the principal or the major hoster of most open source projects right now. And we have a whole bunch of stuff out there right now for if you're thinking about especially application development. I know a couple of you were. There is .NET. If you're into C#, we have what other languages? Python, Ruby, C++, all these examples out there of code. The whole ROS MTConnect integration is actually out there as well on GitHub, so you can actually download that if you want to play around with it with a simulator. There's a Google Glass demo, the one that Joel put together. That's pretty cool. He did a Unity 3D demo as well for Xbox. And he did some Android development. The MTConnect agent that I talked about is all free and open. It's open source. You can just download it. There's pre-built binaries for Windows as well as instructions on how to build it for Linux as well. So you can get that. We have application libraries for parsing data in all these different languages: C#, C, C++, Python, Ruby, Objective-C, you name it. We've got something out there. And that can basically take the real-time data as it's streamed out and turn it into blocks of XML that you can just parse in your application. We have examples of how to do that. We have two labs out there as well, which are useful to get started. There's some work from our studio, which you can use. We actually have some free and open source stuff as well for our studio. We're also, if you're thinking about doing some machine learning examples, I don't know, have you guys heard of this stuff? Like AWS Machine Learning Cloud, and Microsoft has Azure, and they have a machine learning cloud as well. These tools are great, and you can actually take MTConnect data and pump it right into that. Basically, you turn it into like a CSV file or something, and you pump it into like S3 with Amazon, and then load it right into Redshift and do all kinds of wild and wacky things. Microsoft has very similar tools where you can just take like CSV data, pump it in, put your R scripts on there, and you're off and running. We had an example of how to do that in R right here in VRTK. I'll send out all these links later. And that's an example of how we pumped MTConnect data into R. We're going to put more examples out and do some more on analytics and a couple of follow-up webinars as well. And these links here will give you some tutorials on some of that stuff. So to get started, just for ideation, you can the first part of this whole thing, just come up with some creative ideas about what you can do with data and write a 5-page paper. If you're already working on a thesis for a PhD or master's, or I don't know, you have a lot of spare time and you're doing things, just use that. It doesn't have to be anything that is new as far as the work that you're doing. You don't have to start a new project. It can be existing work that you're already doing. So just
Make sure MTConnect is
yeah.
part of it. It needs to be using MTConnect.
Exactly. But if your project is, let's say, or you're thinking about something and it requires data from manufacturing systems of any sort, basically you can say that you can get that data from MTConnect. So the idea is, because it's a standard, it's easy. It just makes it easier to get data and sensor data. So if you're
you can also get low-level data in terms of physics, like for example the data coming from power amplifiers to servo motors.
yes.
Because the thing that's not covered in your examples, but it's like, I think it's the next step for you, right?
We have almost all the power data modeled. So reactive, watts, volts, volt amps, all that junk. Because we actually did a lot of work in sustainability with the standard, so we actually ended up modeling a lot of this stuff out there. So yeah, all the data off of amplifiers. You can even get high frequency data off of amplifiers as well. So again, for ideation, just think about
It
it.
was like toolpath control and the precision stuff. That's the reason I'm asking like for high sample rate.
Mm-hmm. Yeah.
That's also that's great.
Yeah, so you could do like a time series of like, you know, of current if you want to get load,
Yeah.
you know, proxy. Yeah, sure, all that's good stuff. And we'll be following up with some examples of various things. If you want to, yeah, talk to me about, we can get you some, you know, tools,
So okay.
because we have done work, you know, around energy analytics and energy collection. So yeah, we could probably help you out with that a little bit. And so that's the best way to get started. So, and yeah, we'll have all this information online as well as more links and other fun stuff.